In this chapter, as you can see, we are going to look at the frequency response methods. What does frequency response methods means? I think you must have used it in other classes as well. Circuits we use, how frequency changes the response of a system, filters in general, right? Any electrical circuit, mechanical circuit, so on and so forth. They depend upon at what frequency you are giving the input. Different frequencies of the input may result in different response types. And the reason for that is most of the control systems, they have energy storage components, and those energy storage components, they behave differently at different frequencies. And when we are trying to figure out what is the frequency response, that is, at what frequency, what will be the response of the system, generally we are using, not generally, we are using input as a sinusoidal function, because we can change the frequency of sinusoidal function from your function generator, for example. And in circuit analysis, like we discussed the frequency response of different circuits, band pass, low pass, high pass, all those filters. Same goes for control systems. You have different type of control systems. And if your input frequency, signal is a sinusoidal signal, then it's possible that over a range of frequencies, they are going to be behaving as you want them to behave. What do you mean by that? For example, if you're setting a gain, controller gain for the control system, and then when you start running your system, you observe that, hey, I'm not even getting that gain from that control system. And then you observe that the frequency over which you set that gain, you're not operating over that frequency. So it's quite possible that your gain is not going to be what you're planning to set, or you plan to set, because your operating frequency is outside the range over which you are setting the gain. So it's very important that you realize how the system is going to behave over a span of frequencies, so that you can set the range over which your system is going to behave as you want the system to behave, and outside that range of frequencies, you know that the system is not going to operate as intended. So that's what we are going to look at in this chapter, frequency response methods. The behavior of system as you change the input frequency. So the test signal we have used so far, we have used impulse signal. We did not really use impulse signal as much, but we discussed impulse signal. Mostly we use the step signal. We did use ramp signal and parabolic signal in one of the chapters where we were discussing type 0 system, type 1 system, and so on and so forth. But most of our concentration so far has been the response to the step signal for most of the systems. Now, we're going to move away from step signal, because again, a step signal, you cannot change the frequency. It's just a DC signal, either on or off. So if you want to change the frequency, your input signal has to be a sinusoidal signal. And that's what we are going to take in this chapter as how the system is going to behave if your input is a sinusoidal signal. And we are going to assume that the system is at steady state. That is, all the transients are gone, and the system response at any point in the system, the response at any point is a sinusoidal signal, which is changing between two limits, peak values on either side. Initially, even if your signal is input signal is a sinusoidal signal, initially you do have a period over one cycle, couple of cycles, based upon what type of system is that, over which your system is still trying to settle down. That is a transient period. And your sinusoidal is not hitting the range, peak value and negative peak value. It's still trying to settle down between those two values. But we are not going to consider that period. So we are going to consider only when the system has been settled down between the two sinusoidal limits. And then we are going to change the input frequency to observe how the output of the system is changing as you are changing the frequency. All right, so Laplace domain that we've been studying so far, Laplace is comprised of, again, Laplace is comprised of sigma plus j omega. Sigma represent your transient period and j omega represent your sinusoidal response. Now, if we let the transient period go, and if our input is sinusoidal signal, then Laplace domain, we are only going to concentrate on the frequency part, which is j omega. So frequency of the sinusoid, which is j omega. Sigma is exponential decay coefficient, of course, that if your transient is going down, going up, based upon if sigma is positive or negative, and so on and so forth. So we're not dealing with that. We are only dealing with our sinusoidal frequency because our input is sinusoid. And if you're going to change this frequency, then how the response is going to change. That's what we are going to look at. What are the advantages? Some of the advantages using sinusoidal signal as the test signals. Sinusoidal signal with different frequencies and amplitude. You can easily generate those signals using function generator in the lab, actually. Thus, the experimental determination of the frequency response of the system can easily be accomplished. Even for any system, you can give sinusoidal signal and you can plot the frequency response on a spectrum analyzer or even oscilloscope. Design of a system in the frequency domain provides the designer with the control of the bandwidth. Bandwidth is, of course, where the system is going to behave as you want it to behave, whichever way, as well as some measure of the response of the system to undesired noise and disturbances. Transfer function describing the sinusoidal state behavior system can be obtained by replacing S with j omega in the transfer function. And of course, since it's the function of j omega, which is complex, the transfer function will have a magnitude response as well as the phase response, which is, again, we have discussed quite a few times in, of course, circuit analysis, signal processing, if you have taken signal processing, controls, power electronics, and linear integrated circuits, and like in all the courses, basically, wherever we use the complex frequency domain, we calculate the magnitude response as well as the phase response. And that's where, again, you need to have understanding of complex numbers. That's how you're going to write the equation for magnitude response, phase response, and so on and so forth. As we use Laplace transform to analyze the system in S domain, we use Fourier transform to analyze the system in j omega domain, which is a subset of S domain. So Fourier transform, Laplace is the superset, and Fourier is the subset of the Laplace transform. Laplace pair are given by the first two equations. First is the Laplace transform, the second is inverse Laplace transform. And again, we've been using only the table, so there is really no need to do anything with the math, how you're going to get those equations that are in the table, but just to show you that that's the Laplace transform pair that we've been using so far through the table. And then the Fourier transform pair, which is the subset of Laplace transform pair by replacing S by j omega t. That's the Fourier transform pair. Multiple type of frequency response plots. So transfer function can be represented in the frequency domain as, so if you have g of S and you replace S by j omega, then you can write down g of S replaced by j omega is going to be a real part, a function of omega, and an imaginary part, function of omega. And I'm writing here Rw and Xw just to represent R as resistive part, which is real quantity, and X as your reactive part, which is the imaginary value or complex quantity. And this is the rectangular form of Gj omega. If you want to represent this rectangular form into polar form, then it will have a magnitude as well as phase. Magnitude represented by magnitude of G of j omega, and phase is represented by phi omega or angle of Gj omega, whatever you want to write down. Doesn't really matter. angle of GJ omega. And as we know that phase is calculated using the tangent inverse of imaginary over real. However, if you're using tangent inverse function, again, you have to be careful about something. Anybody remember what is what you have to be careful about if you're calculating phase using tangent inverse? Hold on. Yes. If you're calculating phase of a complex number using that formula, which is the basic formula of calculating phase of complex number, what you have to be careful about? Quadrant, yeah. And what is that? Complex plane. Yeah. No, it can be anywhere, but but what you're gonna do, the number can be anywhere in any quadrant. But what you have to be careful about when you're, yes, Rahul, you're saying something? You predicting what? I'm sorry. I don't think I can follow you. In calculator, no. That's not it. Anyone? Yeah. Yeah. And in which quadrant you have to add 180 degrees? Second quadrant. And what else? And third quadrant you subtract 180 from the value that you're getting. And again, we discussed this. I don't know how many times we have discussed this. Because if you're just using tangent inverse function, whether in MATLAB or in your calculator, if it's in the second quadrant, that is R is negative, X is positive, it's going to behave as it is in the fourth quadrant. So you'll have to add 180 degrees because it's going to give you a negative angle in the fourth quadrant. So you will have to add 180 degrees to get the positive angle in the second quadrant. And if it's in the third quadrant, both X and R are going to be negative values, which will make the ratio positive, and it's going to give you an angle in the first quadrant instead of third quadrant. So you have to subtract 180 degrees to properly show that the angle is in the third quadrant, not in the first quadrant, or add negative 180 degrees, whatever you want to call it. Again, in MATLAB, we use angle function, or you can use a tan 2 without adding or subtracting 180 or negative 180. It's going to adjust the angle by itself. And of course, the magnitude is calculated by, phase magnitude of GJ omega is square root of R omega square plus X omega square. So everyone know about the magnitude, how you calculate the magnitude of a complex number. And of course, phase of the complex number with this again, and you don't really have to use this. In MATLAB, angle function works for the angle, and absolute function work for the magnitude. And frequency plot can be obtained either 8.5 or 8.6. 8.6 represents a plot between the real and imaginary part. It is called a polar plot. So this 8.6 right here, if you are plotting real versus imaginary on the complex plane, so you have real axis and you have imaginary axis. And if you're plotting on the complex plane, your real value versus imaginary value, that's going to give you, or you're plotting magnitude versus angle, that's going to give you a polar plot. So there are two types of plots. There is a polar plot, and of course, there is a frequency response plot that you plot against omega or f, both magnitude and phase. Mostly we use the frequency response plots. Well, let's look at one of the systems that we also studied in circuit analysis. Who is going to tell me what type of filter is this? Low pass, why? Well, of course, that's why it's a low pass filter. But why just by looking at the circuit you say it's a low pass? If you don't know it's a low pass filter, how are you going to figure out it's a low pass filter? What is that? Okay, explain a little further. What do you mean by that? Yeah, I know you know that. We discussed it last semester. Anyone else? Because you're the only one who were with me last semester. Say it again. No, again, the question is, if I give you this circuit or any other circuit, and I ask you why it's a low pass filter, why it's a high pass filter, why it's a band pass filter, for simple circuits, how are you going to determine that, oh, it's a low pass filter because of this reason? Yes, Rahul. But that's what my question is. Okay, you know that because you learned that somewhere, right? And likewise, Gabriel said it's a low pass filter, which is okay, it's a low pass filter. But the question is, if you don't know, if I just give you this circuit and I tell you this is a filter, tell me what type of filter is this, and you don't know what type of filter is this, how are you going to figure out what type of filter is this, how it's going to behave as you change the frequency to call it a low pass filter? Oh, you're so surprised, Mustafa. No, I'm just asking you a question. Just a general question, because this is something that I'm assuming, of course, you guys have taken DSP with me. I don't know, we might have discussed in DSP as well, but at circuit analysis, of course, I did not teach for the longest time until last semester, which was not a very good experience, by the way, except you. Yeah, except you. Yes, that is correct. And you want to explain? Okay, so elaborate your answer a little bit more. You're on the right track. Again, she took circuits with me. I don't know when, but a long time ago. You're on the right track, for sure. Okay. All right. Oh, you're on the right track. Okay, now you go ahead and explain. Yes. High means that it's going to act as an open circuit. So whatever input is coming in is going to go to the output. And for high frequencies, yeah, lower impedance. Exactly right. So 1 over 2 pi fc or 1 over omega c is the reactance of the capacitor, as Angelica also mentioned. And at low frequencies, 1 over omega c, omega is low, reactance of the capacitor is high. At omega is equal to 0 at DC, capacitance acts as a short circuit, as we know, 1 over 0, of course, infinite reactance. So whatever voltage is coming in, capacitor short circuit, all the voltage is going to appear across the capacitor because there is no current flow. As you start increasing the frequency, reactance of the capacitor starts going down because 1 over omega c start getting smaller and smaller as omega is increasing. Eventually, when omega hit infinity, 1 over omega c is short circuit, is 0. Capacitor is going to become short circuit at omega is equal to infinity, and the output voltage is going to become 0 because it's going to be in parallel with the short circuit. So at low frequencies, output is high, high frequencies, output is low, and that's how you can determine that it's a low pass filter. If you switch capacitor and resistance position, capacitor in place of resistance, resistance in place of capacitor, then do apply the same logic. 1 over omega c when c is in place of resistor. Initially, capacitor is open, no voltage can go through at the output. Output is going to be 0. And when capacitor is going to become very small, reactance of the capacitor, then it's going to act as a short circuit and all the voltage is going to appear across the resistor, which will be in parallel with the output. So at high frequencies, output will be high, low frequencies, output will be low if you switch capacitor and resistance. And that will be a high pass filter. So this is a low pass filter. Yes, you can memorize the location, but the reason it is low pass filter is because the reactance of the capacitor is acting differently for different frequencies. And that's what you have to observe. And that's what I mentioned a while ago, that if you have energy storage components in a control system, those energy storage components are going to behave differently for different frequency. Capacitor is an energy storage component. Resistor is not. So resistor is not going to behave differently at different frequencies. It does at very high frequencies, at gigahertz, even high megahertz, because of the skin effect. Resistance of the resistor does change, but in general, we assume theoretically that it's not changing. But the reactance of capacitor, of course, is all. Anybody know about a skin effect? No? I thought we discussed that. So, yes. Yeah. Yeah. So at less conductive. Yeah. So at high frequencies, charges start distributing around the skin, or basically around the outer area, or well, inside of a resistor. So as you're changing the frequency, of course, we assume resistance is not changing, but as the frequency increases, all the charges, electrons that are flowing through the resistor, they start accumulating towards the surface area of the resistor. Thus, the effective cross-sectional area of the resistance, it becomes smaller. And the resistance of a resistor, basically, it increases as you start increasing the frequency. So at terahertz, gigahertz, terahertz, the resistance that you're using at low frequencies may behave differently if you're using the same resistance at terahertz or something like that, because your effective cross-sectional area of resistance becomes smaller. Electrons start accumulating towards the surface of the resistance, and start passing through the surface instead of equally distributed over the whole area of the resistance. I mean, that's just on the side note, but generally we assume that resistance is constant. But if you are a telecommunication engineer and working at terahertz frequency or gigahertz, then generally you have to be careful about the skin effect as well. Okay, so what do we have here? Plot the polar frequency plot for the transfer function of the following RC filter. What we have established, that this filter is a low pass RC filter, first order low pass RC filter. First order, why it is called first order filter? Anybody? It's called a first order passive low pass filter. What does it mean by first order? So order of a filter or order of a circuit simply represent, when you write down the equation, voltage, current, what is the order of the differential equation in that? That's represent the order of the filter. Or in other words, the number of reactive elements in the component represent order of the filter. Because if you have two components, RLC, for example, that you discussed in circuit analysis, those circuits were second order system. Because when you write down the voltage equation or current equation, it's going to be d square over dt square plus d. So it's going to be a second order differential equation. So it goes with how many reactive elements you have in the system. If you have only one reactive element, when you write the equation of current or voltage, it's going to be one first order differential equation, and it's going to be a first order system. So if you look at the circuit and see the number of reactive elements, that will be the order of the system. So this is the first order passive low pass filter. Passive because it does not provide any gain in the pass band. Active low pass filter that you must have studied in integrated circuits. Active low pass filter, which are made of generally amplifiers, operational amplifiers, they do provide gain within the pass band, but passive low pass filter, they don't provide any gain within the pass band. So the complete name of this circuit is first order passive low pass filter. That's RC low pass filter. Anyways, enough of the circuit analysis. So we have to do the polar frequency plot. First, we're going to write down the transfer function of this, and then we're going to do the polar frequency plot. Now, as you can see, the input is a function of Laplace, output is a function of Laplace. What is the reactance of the capacitor in terms of Laplace domain? Who remembers this? Laplace in terms of S. One over SC. It's the same thing. Remember, S is j omega. So in the Laplace domain, the reactance of capacitor, I think it's one of the problems we did earlier in chapter 2 or chapter 3. In Laplace domain, the reactance of the capacitor is 1 over SC, and the reactance of your inductor is SL, because S is j omega, remember, right? And again, why this SC? Because the relationship of the voltage and current. If it's the integral relationship or the differential relationship, you apply the Laplace on that integral or differential, and then you're going to get the reactance O is equal to 1 over SC. So if we write down the transfer function, T over S, what will be the transfer function of this? Well, I know that's a transfer function, but what is the expression for the transfer function? Okay, in general, the transfer function is going to be using voltage division, XCS over R plus XCS. That will be the transfer function, which is V2 over V1, V2S over V1. All we are using is what? Voltage division. Now, since we are dealing with the frequency response, S is equal to j omega. So we're going to go ahead and write this transfer function down in terms of j omega. And xc j omega, S is equal to j omega, that's going to be 1 over j omega c over R plus 1 over j omega c, which will be 1 over 1 plus j omega RC. Okay, now remember polar frequency plot. If we go back, polar frequency plot is between real and imaginary parts of the transfer function. That's the polar frequency plot. So we're going to write T of j omega in terms of the real and imaginary. So let's okay. So I have 1 over 1 plus j omega RC. What operation should I perform such that I can write this in terms of real part and the imaginary part? Multiply and divide by the complex conjugate of the denominator. One square is 1, and then j omega RC minus j omega RC is going to be the square of that. That's going to be omega RC square. So I can write this down as the real part will be 1 over 1 plus omega RC square, and the imaginary part will be omega RC over 1 plus omega RC square. Imaginary is negative omega RC, of course. Okay, so we are plotting polar plot, that is real versus imaginary. Let's write down real of T of j omega is 1 over 1 plus omega RC square, and imaginary of negative omega RC square. So that's your complex plane, imaginary numbers, j omega on the y-axis and real number on the x-axis, and of course, numbers can be anywhere. Okay, so you start at omega is equal to 0, and then you move towards omega is equal to infinity. And then you plot real versus imaginary. Omega is equal to 0, real value is going to be 1 when omega is equal to 0. The first real value is at omega is equal to 0. You're going to have a point with the real value 1. What about the imaginary value when omega is equal to 0? 0. So you have 1 and 0, 1 point. So starts at 1 and 0 at omega is equal to 0. When omega is equal to, now the cutoff frequency of this is 1 over RC. When omega is equal to 1 over RC, the real part is going to be 1 over RC times RC will be cancelled out, and you're going to have 1/2. So the real point is going to be 1/2 at 1 over RC. And the imaginary part is going to be, again, omega is equal to 1 over RC. It's going to be negative 1 in the numerator and 2 in the denominator. So negative 1/2. So if I do negative 1/2 here, and 1/2 here, then this will be my omega is equal to 1 over RC. So basically, I'm moving from 0 to this point in this direction. And let's look at when omega is equal to infinity. 3 points should give us complete idea of this plot. Omega tends to infinity. When omega tends to infinity, of course, this is tending to infinity, denominator is large, 1 over large number will be approaching 0. So that's going to be right here. And again, this is hitting infinity, this is hitting infinity. When you have infinity over infinity, what do you do? L'Hopital rules. L'Hopital rule. You apply, you take the derivative of the numerator, derivative of the denominator, and then you again substitute the limit, whatever limit is that. So that's called. So at omega tends to infinity, imaginary of P of j omega you take the derivative of the numerator with respect to omega. That's going to give you negative RC, and you take the derivative of the denominator with respect to omega, and that's going to give you 1 plus, not 1, sorry, 1 is going to be gone with respect to omega. It's going to give you 2 omega RC. Uh, 2 times omega RC, and then the derivative of omega RC, that's going to be, no, it's just going to be 2 omega RC, right? So when you put, so RC cancelled out, when you put omega is equal to 0 again, I mean omega is equal to infinity again, you're going to get 0. So anytime you, after plugging in the limit, anytime you're getting 0 over 0 or infinity over infinity, then you have to first apply the L'Hopital rule. That is, take the derivative of the numerator and denominator and then apply limit again. And still, if you're getting 0 over 0, infinity over infinity, you apply it again and then apply the limit until you get a number. So 0 and 0. And that's omega tends to infinity. So basically, as you are changing the value of frequency, then your polar plot is going from 1 as a real value towards 0 as a real value. And imaginary values are going from 1 again towards 0, and they're passing through negative 1/2. So that's called the polar frequency plot. As you're changing the frequency and plotting the real part of your transfer function versus the imaginary part of the transfer function, how the response is going to look like. And that's how you plot it, the polar plot. All right, what time it is? That's running fast. Oh, it's only 10. I thought it's 10:30. Okay, so we'll keep on going. It's only 10 o'clock. I thought it's 10:30. Okay, so let's move on. Any question about this, by the way? Is it clear? How did I draw it? Yes. Yes, it is. I don't know if there's a built-in. There may be a built-in function, but it's very easy to plot in Octave. The same way we discussed to plot, what was that? Root locus. So basically, what you're doing is when you plug in the value of omega in your transfer function, you're going to get a complex number. Save the real part in one vector and imaginary part in the other vector. And once you have two vectors, then just go ahead and plot the first value of the first vector against the first value of the imaginary vector, and so on and so forth. And you're going to get this plot. Not difficult. You're plotting, again, you're plotting x versus y, right? X is your real and y is your imaginary. That's what you're doing. All right, the next problem, the next example is we are going to plot the magnitude and phase frequency plots of the transfer function of the RC filter, low pass RC filter. So polar plot we plotted, and now we're going to plot the magnitude plot and the phase plot. That is, it is asking us to plot magnitude of T of j omega and phase of T of j omega versus omega or f, whatever you want to plot. So the first thing we're going to do is to write down the expressions for T of j omega. So we don't really have to put down in terms of real and imaginary. We can just use the simplified expression in this case, 1 over 1 plus j omega RC. So T of j omega is equal to, And if you remember from circuit analysis, or you don't remember from circuit analysis, generally we used to write this down as 1 plus j omega over 1 over RC. And this 1 over RC is called what? Breaking frequency or cutoff frequency. That is the frequency at which the magnitude response of the filter is 70.7% of the peak value. That is correct. So that's the cutoff for breaking frequency, where the filter response or the system response becomes 70.7% of the peak value, or 0.707 times the peak value. In this case, peak value is 1, as you can see. When omega is equal to 0, then the peak value is going to be 1. So this can also be written as 1 over 1 plus j omega over omega c. Irrespective which equation you're using, the magnitude expression for this is going to be what? Who is going to tell me what would be the magnitude expression for this one? Go ahead. WRC square, yeah, definitely. I'm just going to use this W omega over omega c square. And the expression for the phase response. Okay. Now, not just inverse time, there's something else as well. How do you calculate the phase of a complex number that is given in a fraction that we discussed? Perhaps in a fraction, if it is given in a fraction. Phase of the numerator minus phase of the denominator. All right, what is the phase of the numerator? So again, this is like, I don't know, 100th time I'm asking the same question. Phase of the numerator is 0. Of course, it's just a real number. It lies on the real axis, which has the phase of 0. All right, so phase of the numerator is 0 minus phase of the denominator. So 0 minus arctan of what? Omega over omega c divided by 1, or simply omega over omega c. So negative arctan of omega over omega c. Why it is so difficult? That, yeah, every time I ask the same question in every class and I don't get any response, except like one student. So magnitude response, phase response, of course, in MATLAB or Octave, all you have to do for magnitude response is use the absolute value and absolute function. Phase response is calculated using the angle function, which gives angle in radians, and you can change that radians into degrees. But generally, we use absolute function and angle function in MATLAB to plot the magnitude response and phase response for different frequencies. But of course, you need to know how to write it. I mean, it's just the polar form. Basically, you're writing the polar form, right? Rectangular form to the polar form, magnitude and angle. Okay, so let's plot this. Insert, oops, insert. Actually, I may not need the negative side that much. So this. So starting at could be plotted against omega or g. So ej omega is 1 over 1 plus omega over omega c. All right, you start at omega is equal to 0 and go towards high frequency. As we know that this is a low pass filter, so we are expecting a low pass curve. At omega is equal to 0, start at 1. The peak value is 1. Important point is cutoff frequency. Omega is equal to omega c. At omega is equal to omega c, this is going to become 1. So you're going to have 1 over square root of 2. What we are expecting, 70.7% or 1 over square root of 2 of the peak value at omega c. And then when omega becomes very large, then the denominator is going to become very large and the curve is going to drop down to almost 0. So the magnitude response is going to be something like this. And likewise, the phase response. We are expecting negative phase because it's negative to arctan. So I'm going to put negative values here. All right, where is going to start at omega is equal to 0? What will be the phase? Omega is equal to 0. The phase is going to be omega is equal to 0. The phase is, come on guys, 0. Omega is equal to 0. Arctan of 0 is 0. Starts at 0. Why it is so hard? At omega equals omega c, what will be the phase? Arctangent of 1. What is arctangent of 1? Negative what? Arctangent of 1. 45 degrees, yeah. So negative 45 degrees. And then when omega is going to become very large, arctan of a very large number, what will be the angle corresponding to a very large number when you take the tangent? 90 degrees, so negative 90. Arctangent is going to go from 0 and 90 degrees, yes, because 0 is at 0, and then when number is going to become very large, then arctangent is going to give you 90, because remember, tangent is sine over cosine. As you are going towards 90 degree, sine 90 is becoming 1, cosine 90 is becoming 0. So when you are taking sine over cosine heading towards 90, the denominator is becoming smaller and smaller, numerator is becoming 1, not bigger and bigger, but it's going towards 1. So if you take the limit, you're going to get 90 degrees, 10 of 90 degrees when the number actually is going to become extremely large. At 90 degree, it does not exist, tangent of course, but close to 90 degrees, it's extremely large value. So your something like that, that's going to be your phase plot. At omega, pretty much at infinity is going to hit negative 90 degrees. So these are the magnitude response versus phase response, magnitude plot versus frequency, and phase plot versus frequency, which is called magnitude response and the phase response of the system. If you're plotting the same in MATLAB, of course, then you need to define, of course, your frequency first. You need to define the value of RC. You can take any value of RC. Let's say if your R is, I don't know, 100 and your C is 100 micro, I don't know, then your cutoff frequency is going to be 1 divided by R times C. Cutoff frequency will be 100 radian per second. So you can define the range of omega. Omega is equal to, if you want to start at 0, 0 to 1, and go all the way up to, let's say, 10,000. If it is 1, you don't have to define the interval anyways. We can define 10 so that it does not have to plot so many plots. 1 is okay, actually. And then you have the equation for t, 1 divided by 1 plus omega divided by omega c. J omega I times omega or omega c. Oh, period. And then to plot the magnitude plot, you have to use the absolute value. So magnitude of t is equal to absolute of t. And the phase plot is phase of t is equal to angle of t times 180 by pi to convert the plot in degrees. And then we can plot, we can just do subplot. So subplot 2 comma 1 comma 1 plot omega comma magnitude of t and subplot 2 comma 1 comma 2 plot omega comma phase of t. Can go for indexing. Oh, so that's gonna be your two plots. Don't look very nice, and there's a reason for that. What is the reason that they don't look very nice? Although the plots are correct, as you can see, it's a low pass, and it's going from 0 to negative 90 degrees. That's one reason that the range is quite large, because the cutoff frequency was simply 100 ohms, I mean 100 radian per second. So all the activity is happening right in this area for both plots generally. And since I'm taking about 10,000 radian per second, then it's just squeezed everything towards left, and the plot doesn't look very nice. The question is, what we can do to rectify this problem? Change the, no, not the step size. That is it. You change the x-axis to the logarithmic scale. You change the x-axis to the logarithmic scale such that every 10-fold of frequency is going to be the same interval, going from 0 to 10 radian per second, 10 to 100 radian per second, 100 to 1000, and 1000 to 10,000. So all 5 section of frequencies, every 10-fold of the frequency is going to divide it equally in the same range with the same length. And once you do that, then you will see the graph is going to be really nice. So let's do that as well. Let's put this, let me copy this real quick. So this is your magnitude. And this is your phase. All right, so let's insert another slide. So anytime you are plotting, most of the time I would say 99% of the time when you're plotting frequency response, you take the x-axis in the logarithmic scale. In MATLAB, anybody remember what do we use in MATLAB? Semi-log x. So we do semi-log x instead of plotting. So let's go, and instead of doing plot, let's do semi-log x. Semi-log of omega is equal to 0 does not exist. I think that's why it is. Let me clear it. Clear. So we're gonna start the range a little. Oops, let's start the range at 1 and go up to 10,000. Omega c is not defined. Okay. Oh, I clear everything. That's why. R C omega c, and then E magnitude of t and phase of t. Subplot semi-log x and subplots. Oh, semi-log. So with the semi-log, that is the x-axis in the logarithmic scale, as you can see, going from 1 to 10, the same length of frequencies as from 10 to 100, 100 to 1000, and 1000 to 10,000. So once you divide the x-axis into equal scale, equal range, then no matter in which section of the frequencies the activity is happening, you can clearly see that okay, in the low side of the spectrum, you have the activity happening, and then finally it dies down, starts going towards 0. It's not 0 yet, but as you know, it starts going towards 0. Oh, it's the negative 90 degrees. Sorry, the 0 is over there, the magnitude. So it's always advisable to, when you're plotting the frequency response, it's always advisable that take the x-axis as the logarithmic scale instead of the linear scale in order to see the response clearly. So these are the frequency response plots for that low pass filter. As you can see clearly, it's a low pass filter. High value at low frequencies, low value at high frequency for the magnitude. All right, now we can take a break. It's 10:22. So let's go ahead and take a break and start in about 10 minutes. Okay, the next topic is one of the most important topics in electrical mechanical engineering, which are called Bode plots. Bode plots are logarithmic plots. Your x-axis we already saw the x-axis is in the logarithmic scale, but in Bode plot your y-axis is also for the magnitude plots. Your y-axis is also in logarithmic scale. So you are plotting 20 log 10 of g of j omega gain in the log scale versus your semi-log x. The important aspect of Bode plots are they are not exact plots, they are approximate plots. So you don't really, of course, before the computers and everything, if you have to plot anything, might be cumbersome to plot points on a graph paper or anything and then connect points. So Bode plots basically gives you an idea of how the frequency response of a system is behaving without plotting the exact values on a graphical paper or anything. And that was the main purpose of the development of Bode plots, such that it gives you an easy way to plot approximate shape of the frequency response of your control systems. And that's what we're going to look at under this topic of Bode plots, how to create approximate plots in the logarithmic scale, such that you don't really have to plot using your computers or anything. Not that you cannot plot using computers, you can still plot Bode plots using computers. Actually, your next project is going to be based on the Bode plot. And there is a function of Bode plot in MATLAB, but that function again plot the exact plot of 20 log 10 of gj omega. It's not the approximate plot. So the goal of the Bode plot is kind of killed if you plot the exact plot, because that's not the goal of the Bode plot. So there are logarithmic plots of magnitude of the transfer function versus logarithmic frequency scale, and the phase plot versus logarithmic frequency scale. So they are estimation or approximation of a frequency response of a transfer function without actually plotting the exact plot using a software or by hand. H.W. Bode, who used them to explain the frequency response of feedback amplifiers, was the one who basically kind of came up with this idea. Magnitude Bode plot, as I said, it is the logarithmic plot. So we take the 20 log 10 of gj omega, we take the gain of the amplifier or gain of the transfer function and represent it as in decibel. So this is decibel. And we plot this decibel scale versus the logarithmic x-axis. And likewise, the phase Bode plot, as you can see, arctan of imaginary of over real that we've been discussing, and that we also plot against the logarithmic x-axis. And the x-axis can either be omega or frequency in hertz. Now, since they are approximate plots, what is the approximation that we use? We will start with the magnitude Bode plot of the not the second order system, but the first order system. And the repeated roots come under this as well. So if you have a function, let's say if your g of j omega is given by k, and let's say j omega plus omega 1 over j omega plus omega 2. Let's say we just restrict right now to this. So you have again k, you have a 0, and you have a pole for gj omega. And we can write this down as k times, take omega 1 out here and write this down as 1 plus j omega over omega 1. And then we take omega 2 as a common factor out and write down as 1 plus j omega over omega 2. So now your Now your modified gain can be represented by K1. Let's say K times omega 1 over omega 2 is your modified gain. And then your 0 is represented by 1 plus j omega over omega 1, and your pole is represented by 1 over j omega over omega 2. So the idea is how you are going to plot the approximation in decibel scale of that function, gj omega. So if you have this and you take the log of this, 20 log to the base 10 of g of j omega, and you take the magnitude of that. When you take the magnitude of this, that's going to be the magnitude of K1, which is K1, magnitude of this divided by magnitude of this. So this is going to come out to be 20 log 10 of K times magnitude of this, which is square root of 1 plus omega over omega 1 square, and then magnitude of the denominator, which is 1 plus omega over omega 2 square. So the idea is to plot this and use some approximation. And when you are taking the log of A times B divided by C, how you can write this down? When you're taking the log, then multiplication become addition and division become subtraction. So you can write this down as 20 log 10 of K plus 20 log 10 of square root of 1 plus omega over omega 1 square, and then denominator becomes subtraction, 20 log 10 of 1 plus omega over omega 2 square. So again, this is the simplest example I'm giving you right now. Yes? K1, yeah, K1. And now we're going to concentrate on each part, and each part is explained right over there. So I'm going to go and then explain each part over there. So this is just a pretext of what I wrote there. I should have started with that and then wrote all those things that I wrote over there. I'll fix that. So the first thing is to plot this, then to plot this, and then to plot this, and then you're going to add all the individual plots together to get the complete plot, because you're adding or subtracting each plot. So let's start with 20 log 10 of K. The first one, Bode plot of a constant term, 20 log 10 of K. In this case, we have K1, whatever. And that's going to be a straight line for all frequencies. So whatever value of K1 is going to be, you take the log to the base 10 of that value, multiply by 20, and that's going to be a constant value. And that constant value is going to be for all frequencies. So you're going to have a straight line that will span over the whole frequency range that you are you're using to plot your Bode plot. So that's going to be a constant value right here. Yes. Second is 0, Bode plot of a 0, which is 20 log 10 square root of 1 plus omega over omega 1 square, square root of 1 plus omega 1 over omega 1 square. So 20 log square root of 1 plus omega 1 omega over omega 1 square. Now this square root, of course, is 1/2. So this 1/2 is going to come here, multiply by 20, that's going to become 10. So 10 log of 1 plus omega over omega 1 square. Now the approximation that we are talking about, this is the approximation. The approximation is that if omega is less than omega 1, if this omega is less than omega 1, we assume that this term is negligible. The second term is negligible. Hence, we just take 10 log of 1 as the approximation of this expression, and log of 1 is 0. So all the values of omega which are less than omega 1, we assume that for all those frequencies, the Bode plot is going to be 0 for that term. So omega 1, of course, is a cutoff frequency, let's say. So up to that cutoff frequency of omega 1, the Bode plot is going to be 0, for that zero term. And when omega becomes greater than omega 1, we assume that the first term becomes smaller than the second term. We ignore the first term, that is, we ignore 1. And when we ignore 1, you have 10 log of omega over omega 1 square. Again, 2 is going to come and multiply 10, and it's going to become 20 log of omega over omega 1. 20 log of omega over omega 1. Now, how this is going to behave? Observe when omega becomes, of course, when omega is equal to omega 1, then this is going to start, because when omega is less than omega 1, it is 0 right here. So when omega becomes equal to omega 1, this term is going to take place. When omega becomes 10 times omega 1, then what's going to happen? Omega 1 and omega 1 will cancel out. 20 log to the base 10 of 10 is 1. So 20 times 1 is 1. When omega is 10 times omega 1, that is 10-fold of the frequency, you're going to get 20 decibel. When omega is 100 times omega 1, when the frequency becomes 100 times omega 1, omega 1 cancel out. It's going to be 20 log of 100. Log of 100 is going to be 2. 2 times 20 is 40. So it's going to be 40 decibels. So as the value of omega increases by 10-fold above the cutoff frequency, you are going to increase the value of the decibel, the value of the gain, by 20 decibel every time. So basically it is increasing. The slope is 20 decibel per decade of the frequency. So that's what we write, 20 decibel per decade of the frequency, and we show that it is increasing by 20 decibel. That's for the 0. That's for the 0 if you have right here. Now what if you have a pole? Now exactly the same thing, except since you have a negative sign with the pole, it's going to go down instead of going up. So the third one is Bode plot of a pole. 1 over 1 plus omega 1 over omega square, which is this term right here. So 20 log 1 minus 20 log of 1 plus omega over omega square, 1/2. 20 log 1 is 0. And we're going to do the same thing that we did with the pole. 1/2 is going to come here, multiply by 20, which is going to become 10. So negative 10 of log 1 plus omega over omega 1 square. And it's going to be the same approximation that we are taking, as long as omega is less than omega 1, or in this case omega 2, what we are taking. As long as it is less than the cutoff frequency, we're going to take the second term to be 0 and the first term is 1, so it's going to be 0. And as it increases beyond the cutoff frequency, every time it increases 10-fold, your value of the decibel is going to become negative 20, negative 40, negative 60. That is, the slope is going to go down by negative 20 decibel per decade for a pole. So this describes the approximation. For the first one is not approximation, but the second one for the 0 and the third one for the pole, these are the approximation for the Bode plot. So again, if you have a transfer function like this is going to result in a constant value. This is going to result up to omega is equal to omega 1 to be 0, and after omega 1 is going to increase by 20 decibel per decade of the frequency, and this is going to be 0 until omega is equal to omega 2, and after omega is equal to omega 2, it's going to decrease by negative 20 decibel per decade. And once you have these individual plots on the graph, then you're going to add all the values and you're going to get your final Bode plot. So let's do, I believe we can do an example. Let's see. All right, before we do the repeated roots, let's do an example first. Let's see if we have something here. Plot the magnitude Bode plot for the transfer function of RC filter that we discussed above. Okay, so that's easy though. The RC transfer function that we had, Tj omega was 1 over 1 plus j omega RC, or 1 plus 1 over 1 plus j omega over omega 1 or omega c, whatever you want to call it. Omega 1 is 1 over RC, which is the cutoff frequency. So if you want to plot the Bode plot for this, versus omega and the magnitude of T of j omega in decibel. Okay. So we have two parts again. We have the first part, which is going to be 0. And then we have the second part, which is going to be, so this is 0. This is going to be 10 times log 1 plus omega over omega 1 square. So the first part is 0, the second part is negative 10. So for the second part, as long as the frequency is less than omega 1, omega is less than omega 1, we assume this term to be 0, and we are going to have 10 log of 1, which is going to be 0. So let's say this is omega 1, and it is going to be 0 until omega 1. And then let's say this is 10 omega 1, this is 100 omega 1, 1000 omega 1, so on and so forth. And as omega increases beyond omega 1, we assume one term is 0. So this is going to become negative 10 times 2, 20, negative 20 log of omega over omega 1. And it's going to drop negative 20 decibel per decade. Negative 20, negative 40. So it's going to be negative 20 at 1 decade of frequency, which is 10 omega 1, negative 40 at 100. So it's going to go. And we have to show that the drop. So this is negative 20 decibel per decade. And that is going to be your Bode plot for the first order RC low pass filter that we had. Again, this is an approximate plot, because if you want to plot the exact plot in decibel, you're going to have a curve over here. It's going to go like this, and then this. You can plot it using MATLAB, of course. So you're going to have a curve over here. It's not going to be an abrupt change, but it doesn't really matter, as I said, because again, Bode plot is, it gives you an idea of how the frequency is changing. It does not really need to have the exact values of the phase or the magnitude versus the frequency. Okay. Let me see. Now we can do this example, and then we can go back and look at the multiple plots. Because I don't want to do multiple plots. And yeah, 2 repeated roots, 2 repeated poles. This is okay. All right, let's do this example then. Example, next page, right here. Derive the transfer function of the following circuit. This is a transistor amplifier, and draw its magnitude Bode plot. So we have R1, we have R2 dependent source. That's an amplifier, of course. This is transistor, basically. This right here is a transistor. And then you have C2, you have R out, and V out. This is what 5 kilo ohm on 10 nanofarad, and 4 kilo ohm and 1 kilo ohm. All right, we're going to convert everything first of all into j omega. So R are not going to change, of course. C is going to change into X of C. Let's call this X of C. C2, but there's only one C, so I'm just going to call it, instead of calling it C2, we can just call it C. That's going to be X of C, 1 over j omega C. All right. So what will be the transfer function of this circuit? How are we going to find the transfer function of this circuit? We are looking for V out j omega over V in j omega. V out j omega over V input j omega. How are we going to find the transfer function of this circuit? Vx. Now V out here, of course, this is all in parallel. So you can find the parallel combination of these two, which will be, let's say, Z, which will be the parallel combination of XC and R out. And then the output voltage will simply be what? Anyone? V out will simply be negative ID times Z. Ohm's law. Negative because, of course, current is going from bottom to top, but the voltage polarity is from top to bottom. And ID depends on Vx, and Vx is on the left hand side of the circuit. So ID is negative Vx times Z over 200. All right. And how we can write down input voltage in terms of Vx, or Vx in terms of input voltage, from which we can calculate input voltage in terms of Vx. Vx is equal to V1, V input, times R2 over R1 plus R2 ohms voltage division. So V input is Vx R1 plus R2 over R2. Oh, there's a, oh, that's why there was C2. Oh, I didn't see that. That's why I put, so this is XC2. So let's go ahead, and I didn't see that C2. Let's go ahead and change that real quick. Okay, so that's going to be XC1. XC1. All right, same basically. So Vx is equal to R2 over R1 plus R2 plus XC1 times V input, and V input is equal to Vx R1 plus R2 plus XC1 over R2. So Vx and Vx will be cancelled out, and the transfer function is simply z over 200 negative z over, and I'm going to put so negative z, and I'm going to take R2 on top, negative z times R2 over 200 R1 plus R2 plus x of z. Question up to this point? It's clear? Okay. Now z is the parallel equivalent of these two. So 1 divided by 1 over R out plus 1 over XC2, which will be 1 divided by 1 over R out, and XC2 is 1 over j omega C2 plus j omega C2. Go to the next page. So h of j omega is 1 over so R out over 1 plus j omega RC2. R out negative R out j omega C2, and R out is going to be dropped. So that's going to be your Z. And then, R2 over here as well. So R2 R2 times R2 times R out 1 plus j omega C R2. Yeah, that's going to be here. Negative 200 R1 plus R2 plus XC. And times 1 over R1 plus R2 plus XC. 1 over j omega C. All right, let's simplify this. I'm gonna have j omega c1 over 1 plus r1 plus r2 times j omega c. So I'm trying to write this down in terms of poles, zeros, and a constant values. All right, this I'm gonna bring R naught C2 as a common factor in the denominator. And I'm gonna write this down as 1 over R naught C2 and write this down as, no, sorry, not R naught C2. It's gonna be let me see. I want to write this down as omega over omega. It's going to be omega over omega 1. Omega 1 will be 1 over R naught C2. So let's write this down. 1 divided by 1 plus j omega over 1 over R naught C2, which will be omega 1 times j omega over 1 over C1 1 plus omega 1 over j omega C. So let's clean it up a little bit. Let's calculate what are these values so that we can we can write it down in terms of a transfer function with some values. So let's write down. Let me see what are the values. R1 is equal to 1k, 1 exponent 3. R2 equals 4k. And C1, 20 microfarad. C1 is 20 exponent negative 6. And C2 is 10 nanofarad. And R out is 5k. Okay. And now I go here. R naught R2 over 200. So let's say K is R naught times R2 divided by 200. That's 100,000. Negative 100,000. All right, 1 over C1. That's 50,000. And then the denominator is 1 over j omega, 1 over R naught C2, R naught times C2, which is 1 divided by that. So inverse of that answer. So 20,000. So I have 1 plus j omega over 20,000, which is this. And for this, let me see what is that. 1 divided by R1 plus R2 times C1. That's simply 10. 1 plus j omega over. So this is the transfer function that I'm getting in terms of your zeros and poles. See if you're getting the same or not. We can cancel this out. Actually, this is 50,000 and this is 100,000. So we can kind of manipulate that. It's going to become 2. 50,000 times 2 is 100,000. Just let me make sure it is correct. R0, R2 over 200, 1 over 1 plus j omega R0 C2 times j omega C1, j omega C R1 plus R2. Okay. Let's make sure if I'm not making any mistakes somewhere. So we're gonna do the Bode plot of that function. It has 1, 0, and it has 2 poles. And I hope my calculations simplification is correct. If I made a mistake somewhere, then it's gonna be I mean, we can still do the Bode plot. Process is not gonna change. The values will change if I made a mistake somewhere. I hope I did not, but who knows? Does it look correct? Or is there a mistake somewhere? You getting the same? Or you getting different? You getting same? So we have 1, 0, and we have 2 poles. So let's do the Bode plot of that. Magnitude Bode plot. Magnitude means, of course, we're going to drop this negative sign. Magnitude of the numerator, which is going to be 2 times omega. And then magnitude of the denominator. That's my equation that I'm going to be using to plot the Bode plot. I'm sorry? Square, yeah. For both of them, because they are poles, they're in the denominator. So when you take the 20 log of this whole thing, and magnitude of that, so you take the, I'm sorry, distributing. So okay, let me go back. So your magnitude, let's write down first. Let's go back and then write down the magnitude expression first, and then Bode plot expression, so that it becomes clear. Okay, so first write down the magnitude of h of j omega. So magnitude of h of j omega is going to be magnitude of the numerator divided by magnitude of the denominator. The magnitude of the numerator is 2 times omega. And magnitude of the denominator are the square root of 1 plus omega over 20,000 square root of this. So divided by, I'm going to put down the 10 first and then 20,000. So that's the magnitude of h before we apply the 20 log 10, right? Now let's apply 20 log of 10. That is the Bode plot. Log n of the magnitude of h of j omega. And decibel, which is 20 log 10. So this is 20 log of 2 omega over a square root of the first one and a square root of the second one. This is the first one right here, and this is the second one right here. So again, apply the log rule, 20 log of numerator. And we can even divide the numerator into 2 times omega. So it's going to be 20 log of 2 plus 20 log of omega. And then the denominator. So when you're applying log on the denominator, each one of them is going to be subtracted because in the denominator they are multiplied by each other. So that's going to be subtracted when you apply the log function. So that's going to be negative 20 log of the first one, which is this, and minus 20 log of the second function. So log of A over B times C. If you apply log of A over B times C, apply the log, it's going to be log of A minus log of B minus log of C. That's what we are doing over here. Log of A divided by B times C. So log of A minus log of B minus log of C. And log of A, of course, is multiplication, so we divided that into addition, two of them. Log of 2 plus log of omega. Now log of 2 is a constant value. What is the log of 2 times 20? 20 times log 10 of 6.02. So 6, let's just do 6. 6 decibel plus 20 log omega minus 20 log square root of 1 plus omega over 10 square minus 20 log. Okay, we don't have to go further than that. We can just plot the Bode plot. So we have 6 decibel. That's a constant value over all frequencies. This, how it is going to change? As omega is going to increase, omega, of course, as it's going to increase beyond 0, and log of 0 does not exist. Let's say omega of 1. Omega of 1 is 0. So as it's going to increase when omega is 1, then it's going to increase to 10 to 1000. Every time it will increase tenfold. It's going to increase by 20 decibel per decade. And likewise, every time they're going to go beyond 10 and increase tenfold, this is going to decrease by negative 20 decibel per decade. Every time this is going to go beyond 20,000 and increase tenfold, this is going to decrease by negative 20 decibel per decade. So we have 4 lines that we're going to draw, and then we're going to add all those lines. Okay, the first line is 6 decibel. So let me see. There's 20, there's 40, there's 60, negative 20, negative 40, negative 60. And let's go ahead and start at frequency 1, 10, 100, 1000, 10,000, 100,000, 1 exponent 5, 1 million, 1 exponent 6, and so on and so forth. So we are increasing frequency by tenfold and keeping the interval to be equal between each tenfold of the frequency. Now the first one is 6. So 20 is half is 10, and 6 is somewhere over here, let's say 6. That's going to be on all frequencies, at all frequencies. That's a constant. And draw it with the dotted line, because the solid line will be the complete Bode plot. Dotted line will be the individual Bode plots corresponding to each element. The second is 20 log of omega. So 20 log of 1 is 0. Let's say start from 1. 20 log of 1 is 0. 20 log of 10 is 20. 20 log of 100 is 40. So it's going to increase by 40 decibel per decade, 20 decibel per decade. And this is for 20 log of omega. The third one is going up to 10 radian per second. It's going to be 0, and then it's going to drop by negative 20 decibel per decade. So let's say the third one is going to 10, and it's going to drop by, let me use the gray line, it's going to drop by 20 decibel per decade. So 20, 40, so it's going to go 0 until 10, and then negative 20 decibel per decade, and this corresponds to 20 log of square root of 1 plus omega over 10 square. Yes. Yeah. Okay. So okay, I have to show you again this. So that's going to be, let's say, 20 log of 1 plus omega over omega 1 square, right? Negatives. So that's going to be 1/2, sorry. So this is a square here, and this is 1/2. It's a square root. Okay. So that's going to become 10 first, 10 log 1 plus omega over omega 1 square, and then you apply the approximation as long as it is less than omega 1. Yeah, so as long as then it becomes greater than omega 1, then you drop 1. So it's going to be omega over omega 1 square, and then this 2 is going to come here. Right? All right, and the last one is our 20,000. So it's going to 20,000 will be up to 20,000 will be 0, and after 20,000 it's going to drop by 20 decibel per decade. So let me just use the same gray color. So 10,000 is here, and then 20,000 will be somewhere close to 10,000. Let's say this is 20,000. 20,000. So it's going to go to 0, 20,000, and it's going to drop 20 exponent 2 exponent 5, 2 exponent 6. So it's going to drop 20 decibel at 2 exponent 5, 40 decibel at 2 exponent 6, and so on and so forth. So slope is still going to be the same. Slope will still, you have to show the slope that this is 20 decibel per decade, and this line corresponds to 20 log 10 of square root of 1 plus omega over 20,000 square. Negative, negative, and negative. So these are the 4 lines corresponding to those 4 factors in this equation right here. If you have any question up to this point, please go ahead and ask me. Any question? No? Making sense? No? Somewhat? Yeah. Different classes, very different classes. No, you did not do Bode plot and circuit analysis. Yeah. I don't think so. Huh? We did that in briefly in the integrated circuits, first order Bode plots in chapter number 1 or 2. That was only first order Bode plot, briefly. That was just one topic, a small topic. But it was not combination of different factors though. Okay, we're gonna do some more problems, so you will eventually start getting it. All right, so now what we are going to do, we are gonna add all these because you're adding all these factors, adding the first two and then subtracting the last two. So we created the individual plots for each one, and now we're gonna add all of them together. So I'm gonna use my red pen, and when we are adding, we have 6, and then this is increasing. So basically, up to, let's say, up to 10, this is 0 up to 10, and this is 0 up to 200,000. So up to 10, we start with 6, 6 plus 0. So we start with 6, and we increase up to 10, 20 decibel per decade. So it's going to go up to 26. And at 10, it's going to go up to 26. So we are adding this line 6, and we are adding this blue line, which is increasing by 20 decibel per decade. Now at 10, what happens now? This is increasing by 20 decibel per decade, and this is decreasing, start decreasing by negative 20 decibel per decade. So they're going to cancel each other. This slope, 20 decibel, and this slope, negative 20 decibel. They're going to cancel each other. So the only thing that will be left is now that is going to stay at 26, because these two cancel each other. So this value is just going to stay at 26. That's not going to change until it will hit or 200,000 or 20,000. Once it hit 20,000, now you have negative 20 decibel per decade, negative 20 decibel per decade, and positive 20. So these two already have cancelled each other. Now there's nothing for this one to be cancelled out. So now it's going to start going down by negative 20 decibel per decade. So it's going to go to 6 again at 2 exponent 5. Let's say 2 exponent 5, and it will keep going down. All you have to show is the slope. So start going down at negative 20 decibel. Okay. So this solid red line is your Bode plot of the system. The dotted lines are the individual Bode plots, and the solid line is the Bode plot of the complete system. And from this Bode plot, you can say that this control system is going to have constant gain from 10 radian per second all the way up to 200,000 radian per second. It's going to offer pretty much constant gain, which will be about 26 decibel. So if you're operating the system between that frequency range, you expect that this system is going to provide you about constant gain. After 20,000, the gain is going to start declining by negative 20 decibel per decade. Let's do the Bode plot in MATLAB to show you the difference. Let's see. I think it's Bode. Help Bode. I thought I already package load. Okay, let's see. Bode system. So let's do Bode system. So system is equal to transfer function. And again, Bode plot, as I said, this is going to, let's see, system is how they're defining the system. I think they're defining the system as h of s. Let's see, the system that we have. We define it. So that's going to be s over 50,000, or right here. That's going to be 2s let me see. So that's going to be 2 negative 2s over 20,010, and then s plus 20,000, s plus 10. So that will be the equation for the system. 2s times 20,000 times 10. So 40,000 times 10, 400,000 s. That's going to be 400,000 s. Negative sign doesn't matter because you're doing the magnitude. 400,000 s over s plus 220,000 over s plus 10. That's your transfer function. If you replace j omega by s, that is. So let's see. I don't remember exactly. I'm assuming this is how it's going to take it, but let's try. So that's going to be 400,000 comma 0, and denominator is going to be s square, and then 200,000 no 200 20,010 20,000, no, that's too much. 20,010 and then 200,000. All right, 200,000. Let's see if it works. I don't think I've used Bode much here. So let's see, Bode of system. All right, it did work actually. Okay, so observe our plot and this plot is very close to each other. Come on. All right, there you go. Magnitude Bode plot. It started at 6 decibel. It went all the way up to, I believe this is 26. I'm assuming it's 26 decibel. Let's see if I can find this. Let's see what value it is showing. Yeah, 26 decibel right here, 26.261 at the bottom. So that's 26 decibel line. And then it starts going down at 20,000 frequency. So now this is, again, this is the decibel plot. Looks similar to what we plotted, but this is the exact plot though. This is not the approximate. Bode is approximate plot because you can see the curves are so smooth. For Bode, curves are never smooth because it goes until it's going to go to 0 until the frequency, and then it's going to start dropping or start rising. So at the cutoff frequencies, if your curves are smoother, then you're plotting exact plot. But if your curves are not smoother, then you're plotting the Bode plot, which is the approximate plot. But at least it's going to give you an idea, and this is how it should look like. and then of course you can kind of make the curve not smoother. At least you can check your work against this. This is the phase Bode plot for the same. We're going to come to phase Bode plot most likely next week. It's 11:44 already. But that's our exact magnitude Bode plot. Let's go ahead and save this as well. Copy. Put the code as well. The other thing that you can do, of course, you can see Bode, but for Bode, of course, you have to write the function in terms of S, what I did right here on this slide. Saving. Come on. Okay. So to use Bode, of course, a function that you have to write in terms of S, polynomial over polynomial. That's what I did over there. But if you don't want to use Bode, you can still plot h of, you can still plot this thing, whatever equation is this, change the range of omega and take basically your the log. Let me show you that as well. So basically what you are doing here, let's say we have this equation right here. Of course, you're going to take the range of omega. Omega is equal to, let's say, 1, 1 and or 10. Let's take 1. That's okay. So 1 to what range did we get? 20,000, 200,000, 200,000. Let's see. And your h is negative 2 times omega times I, and 1 plus I times omega divided by 20,000 times 1 plus I times omega divided by, let's see if I'm writing it correctly. So 1 plus this parentheses, just, I don't think I need this. Or do I need this? 1 plus j omega over 20,000. Yeah, I do need it. Times, no, I don't. 1 plus j omega over 20,000 times 1 over j omega over 10,000. Okay. And then this is one factor, and this is the other factor, and this is the last one. Okay, so let's see. I hope I'm not making any mistake with the parentheses here. Okay, it works so far, so let's move on. Okay, and now basically you are plotting the Bode plot, which is the decibel plot. So you're gonna take h, let's say h decibel is equal to 20 times log to the base 10 of h. And now you can plot semi log x omega comma magnitude of h decibel. And let's see if it gives us Oh, absolute value, not magnitude. Absolute value of h decibel. Not giving the the same values, starting at 16. Why starting at 16? Missing something. I mean, it's showing kind of curve is correct. X-axis values are not correct though. I'm not sure why. Let's see. Am I writing it correctly? -2 J2I divided by 1 plus j omega over 20,000 times 1 plus j omega over 10 whole divided by that -j2. Not sure why it is not 1 to 20,000. Okay. The plot, the shape of the plot is correct, but the scale is incorrect. I don't know why. Going up to 37 or something, starting at 16 something, 15 something. Yeah, around 16. Setting 10. Should have started at 6 instead of 16. And I don't know why. But basically, that's what you have to do. I don't know. I'll figure out why it is not giving you. But basically, that's what you have to do. This is your age. You take the decibel of that age, and then you plot the decibel versus semi-log scale. That's what basically your Bode plot is. Approximate, not approximate, but the exact Bode plot. The Bode function is giving the correct plot, but this is not. I wonder why. Anyways. All right, question. So again, if you, as a designer, as I said, as a designer, if you're designing the system, you better be operating the system for a constant gain within 10 radian per second up to 20,000 radian per second. Outside that range, you can expect your system is not going to perform as expected. All right, guys, we can take another break, about 8 minutes, and then do some more. Again, this will be continued next week. We still have a lot to cover. What I'm going to do right now is I'm going to go back actually and discuss the topic that I left, which was if you have repeated roots in the poles or zeros, then how do you tackle those repeated roots in the Bode plot? So that's what we're going to discuss. If we have time, we're going to do one more problem, and then that will be it for today. So let's take about up to 12 o'clock break, and then try to finish this whatever we want, whatever we can today. Okay, guys, so the last thing that we have to do today is look at if we have repeated roots, repeated zeros, or repeated poles in the transfer function. They're very simple to treat in Bode plots because anything that is a square or cube, of course, when you're taking the log, you just multiply the power by the gain of the log, the logarithmic scale. So if you have if you have two poles, repeated zeros, 1 plus omega over omega 1 square, magnitude of, so if you have basically, grab the pen. So if you have g of j omega, let's say, k times 1 plus j omega over omega 1 square, a term like this, which you can write down k times 1 over 1 plus j omega over omega 1 times 1 plus j omega over omega 1. So when you take the magnitude of gj omega, it's going to be magnitude of the first 0 and the magnitude of the second 0, and both of them are of course the same because you have repeated zeros, which we can write down 1 plus omega over omega 1 square. And when you take the convert it into decibel scale, 20 log of this, it will simply be 2 is going to come here and multiply here to 40 log of 1 plus omega over omega 1. So basically what's going to happen, as long as your value is less than 1, as we discussed, it is going to be 0. We assume the second term to be 0, and when your frequency increases beyond omega 1, then only the second term will be considered, and it's going to become 20 log of omega over omega 1 square, which will be 40 log of omega over omega 1. So that means the magnitude of that line is going to increase by 40 decibel for every 10-fold of frequency. Similarly, if you have 2 poles, repeated poles, then it's going to drop by negative 40 decibel per decade. And this we can extend for 3 zeros or 4 or 3 poles. That is going to, if you have 3 zeros, it's going to be 60 decibel per decade. It's going to increase. And if you have 3 poles, it's going to be negative 60 decibel per decade. It's going to increase. So all you have to do is to, based upon how many poles or zeros you have at the same point, you just have to multiply the 20, the slope of the line, by that many, the number of poles or zeros that you have. This is repeated. Let me delete this slide. So based on that, we have, I think, this problem, but we're going to do the last problem today. Draw the Bode plot of the following transfer function: gs 200 s plus 1000 s plus 10 square s plus 100. Okay, the first thing that we are going to do is to write it down in terms of gain times 0, 1 plus s over cutoff frequency, and so on and so forth. So let's write this down as 200 times 1000 and write the 0 as s over 1000. Because we have to write this down as j omega over omega 1. S, of course, is going to be j omega. And do the same thing in the denominator. So we have s times 10 and s times 10. So this, I'm going to take the 10 out from each one of them. So 10 times 10. 1, not 1, sorry. 1 plus s over 10 square. And then I'm going to take 100 out from here. 1 plus s over 100. So first I'm going to write this down in terms of s over omega 1, s over omega 2, and s over omega 3. (200 times 1000), so 100 times 10 is 1000, so I'm going to cancel this 1000 by 1000, and 10 times 20 is 200. So 20, 1 plus j omega over 1000 over 1 plus j omega over 10, 1 plus j omega over 100. So you're going to put down everything in terms of gain times 0 divided by poles, the product of all the poles. All right, now when you're doing the Bode plot, we're not going to write the equation. We're just going to jump from here to Bode plot. Let me ask you this. When you're doing Bode plot, how you're going to approach this system as far as Bode plot is concerned? What you're going to do first? Constant. Okay, so what will be? All right, so that will correspond to what value? 20 log 10 of 20. 20 log 10 of 20 for all frequencies. So that's the constant gain. 20 log 10 of 20 for all frequencies. What about the zero? How are we going to treat that zero that you have? No, just the zero that you have, this term right here. How are you going to treat this term in the Bode plot? It's going to be 0 until 1000 radian per second, and then it's going to start increasing by 20 decibel per decade after every 1000 radian per second. Well, we will. I mean, if you're writing equation, that's gonna how it's gonna turn out to be, right? But if you wanna jump directly from here to Bode plot, that's what I'm asking. If you if you understand how you're gonna do it, you can ignore that equation then. So this term is going to be 0 until 1000, and at 1000, starting at 1000, is going to increase by 20 decibel per decade of the frequency. So at 10,000 radian per second, it's gonna be 20 decibel. At 100,000 radian per second, it's going to be 40 decibel. How are you going to treat the pulse? So this is going to start at 10. Up to 10 is going to be 0. It's going to start at 10 radian per second, and then it's going to go down negative 40 decibel per decade because it has the square term, right? And similarly, this is going to be 0 until 100, and then it's going to go down by negative 20 decibel per decade. So just from the transfer function, you can jump from the transfer function directly to the Bode plot. So let's go ahead and we can do it on this side actually. So this is going to be G J omega, magnitude, Bode plot, decibel. Let's see, this is 20, this is 40, this is 60, negative 20, negative 40, negative 60. And let's start at, so we have 1000, 10, and 100. We can start at 1, then 10, 100, 1000, 10,000, 100,000, and so on and so forth. So 20 log of 20. What is that? 20 log of 20. 26. So that's going to be 26 right here. 26. That's constant for all frequencies, over all frequencies. Okay, this is going to go until 1000. It's going to be 0 until 1000. And then it's going to drop. I can use another marker. And then it's going to drop by negative 20 decibel, positive 20. It's going to increase by 20 decibel per decade. So at 10,000, it's going to be 20. At 100,000, it's going to be 40, something like that. Totally destroyed it. So this this is 1 plus j omega over 1000 Bode plot. This is going to go up to 10. And then it's going to drop by negative 40 decibel per decade. So at 100, it's going to be negative 40. 2 points are good enough. And then I'm going to connect that. Negative 40 dB per decade. And then this is going to drop by negative 20 decibel per decade after 100. So less slope. Negative 20 dB per decade. So these are the 4 lines corresponding to the 4 factors. And then we're going to go ahead and add all of them together. All right, starting at 26, it's going to be constant until 10. At 10, it's going to start dropping by negative 20 decibel per decade. So when it's going to get to 100, negative 40 decibel per decade, sorry. So when it's going to get to 100, it would have dropped 26 minus 40, negative 14, right? Negative 40, right? So that's going to be somewhere negative 10, negative 14, let's say it's here somewhere, negative 14. So when it gets to 100, it's going to drop up to negative 14. Slope is negative 40 decibel per decade. I'm going beyond 100. Negative 14 is at 100. So this right here. Right. Okay. So the slope of this line and slope of this line should be the same. Negative 40 dB per decade. Okay, what's going to happen between 100 and 1000? It's going to drop by negative 60 decibel per decade, negative 40 because of this, and negative 20 because of this, because there's nothing else to compensate for these two in the positive side. So it's going to drop, it's going to become much steeper, negative 60 decibel per decade between 100 and 1000. So 100 and 1000, it's going to drop by negative 60 decibel per decade. So negative 60 and negative 14 is negative 74, right? So it's going to go to negative 74. It's hard to see that the slope is changing, but it will change. And then after this, when you hit 1000, the slope positive 20 decibel and this negative 20 decibel will cancel each other. And only the negative 40 decibel will be left. So it's going to change the slope again to negative 40 decibel per decade. And that will keep on going. Basically, the slope is going to be the same as this line. So my slope is a little different, but it's going to be the same as this one. So that's going to be the magnitude Bode plot for this function. Let's use the Bode function and see how it It does it. All right, so we have 200s. And then 200 times 1000. And the denominator, I'm just going to use the poly function. Poly. I have negative 10, negative 10, and 100. 3 roots, negative 10, negative 10, and negative 100. I don't think I need to use the square bracket here. It's going to create a bracket. Let's see. All right. Poly function, of course, from the roots, poly function is going to convert roots into the polynomial. So if you know the roots, then you can, instead of multiplying it, you can just use the poly function and create the polynomial from the roots. And then we do the Bode of sys1. All right. Again, it's hard to kind of see, but it has starting at 26 decibel, as you can see, and then at 10, it is started going down by 40 decibel per decade, and then it's going to become 60 decibel per decade, and finally, again 40 decibel. So you can see kind of the slope is getting steeper over here, and then again getting negative 40 decibel. Okay, so this is the Bode plot. And I think the next topic seems like it is the phase Bode plot that we're going to discuss next week. So we have to discuss phase Bode plot, and we have to discuss the Bode plot of the second order system, the underdamped systems. I am going to give you a project from this, which will be creating the Bode plot of what we have discussed so far. Basically, if you have first order zeros, first order poles, or repeated poles, or whatever, then how you're going to create the individual lines and then connect those lines. So it's going to be a project based on that I'm going to post, basically. So keep an eye out when I post it. Of course, I'm going to send you an email as well.